All right, so today we are moving on to our new unit on exponential functions. Okay, so far this year, we've spent a lot of time looking at quadratic functions, and then we spent a lot of time looking at square root functions, which are basically like, they're sort of like inverses of each other, right? They're not sort of, they actually are inverses of each other, right? So we have looked at functions where we've had something like x to the second power or x to the third power. And then we looked at their inverses, which would be like the square root of x and the cube root of x, right? So what we're doing now with exponential functions, instead of having the variable in the denominator like we had here, now we're switching it so that you're going to have some sort of a whole number as your base, and your variable will be the exponent. So we're going to look at things like 2 to the x and 3 to the x power. Okay, so let's talk about kind of what the difference between these guys is. Okay, so let's take a minute and just sort of compare. What's the difference between x squared and 2 to the x? Okay, well, let's think about what happens to these numbers. So quick little table of values, right? 1 squared is 1, right? 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared, 36. Great. Okay, so that's pretty easy enough to deal with. So what we're doing here is, instead of squaring numbers, we're doing powers of 2, right? So when x is 1, 2 to the first power is 2. 2 to the second power is 4. Similar. There's not really a ton of difference at the beginning. Okay, at 4, we're in the same spot. Okay, but if you kind of pay attention to what's going on with these numbers here, right, they're going to keep getting bigger, but not all that fast, right? Our next numbers are going to be like 49 and then 64 and then 81, right? But the next numbers over here are going to be 128 and then whatever 128 times 2 is, that's 200 and something, right? And then that's up to like in the 400s. So because these guys are doubling, this one is going to grow a lot faster than this one does. So they start out pretty the same, but exponential functions grow a heck of a lot faster than any kind of variable raised to an exponent does. Okay, so that's kind of the key difference between the two of them. So today we're going to start out by just looking at our good friend graphing, which we've been doing since the beginning of this year, right? And it's going to be very, very similar to what we've done. All the transformations are the same. Okay, we just have different base functions we're going to look at. Okay, so the definition of an exponential function, y equals a times b to the x power. A and b have to be real numbers. Okay, so no imaginaries allowed. And b has to be greater than 0, and it can't be 1. Okay, well, why is that? Okay, well, because if b is negative, that kind of just messes up the form. And we're going to look later about what's going to happen with that and how that'll be different. Okay, b can't be 1, because if b was 1, this would be stupid, right? 1 raised to a whole bunch of different powers is always going to be 1. So this is just, it makes it trivial if that's the case. Okay, and this is just to adjust it, and we'll see that in a second. Okay, so let's take a look really quick, make a table of values. We kind of already did this, all right, but we're going to kind of start in the middle. We didn't talk really about negative exponents here, right? So 2 to the 0 power would be 1, right? 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. Probably about all we're going to fit. Right, but when we start taking a look at our negative values of x, 2 to the negative 1 power, negative exponents make things flip, right? So 2 to the negative 1 is the same as 1 over 2. Okay, 2 to the negative second power, right? Well, the 2 part squares it, so you get 4, just like we did down here. But the negative flips it, so this is going to be 1/4. 2 to the negative 3, well, 2 to the third power is 8, but the negative makes you flip it. So this would be 1 over 8. So as you kind of look at this table, you should see there's a sort of symmetry here, right? You get this 1 in the middle, and then it's 2 versus 1 over 2, 4 versus 1 over 4, 8 versus 1 over 8. And as you think about it, that's going to keep going forever. You're always going to have that kind of symmetry. All right, so let's take a look at But let's think about this, okay? So when we think about what's going to happen here, this is getting smaller, right? But are we ever going to get to 0? Think about what's happening in our table, right? We said that we've got this reflective pattern where it's just going to keep being 1 over whatever. These numbers are going to keep getting bigger forever, which means these numbers are always going to be 1 over some number that's going to get bigger forever, right? Which means as these guys are getting bigger, these guys are getting smaller. But we're never actually going to get to 0, right? You can't take 2 and raise it to a power and get an answer of 0. So what happens is as you go in this direction, this graph is going to keep approaching the x-axis, but never actually get there, okay? So on this side, your graph is going up like normal. It's going to get steeper and steeper and steeper as you go. But on this side, it's kind of leveling out, right? It's not actually leveling out. It's never actually going to be level. It's going to keep going down forever, but it's never going to reach this x-axis, okay? So that is a special thing in math called an asymptote, okay? So this line right here, which in this one is on the x-axis, I'm drawing it a little bit below the x-axis just so you can see it, okay? So this line right here, that is called an asymptote. So it's asymptote, asymptote, okay? And what that is it's a line that your graph continually approaches, but never actually gets to, okay? So that is a feature that certain graphs have. So the first thing that you want to notice, okay, is that your graph, so the graph never reaches the x-axis, okay? That is called an asymptote. All right, and the definition of what an asymptote is, okay, it is a line, okay, that the graph approaches but never reaches. So a line that the graph approaches but never reaches. Okay, and you're going to want to make sure you know that word. Okay, so that's an asymptote. So that's the first thing I want you to notice. The second thing that I want you to notice is just that, like, this graph in this quadrant here, right over here, it's kind of flatlining, but over here, it's going to go up really, really sharply, right? Think about what these numbers are going to be. The next one, I'm going to be up at 16. So I'm going to like double that height. My next point's going to be like here. And then the next one is going to be like way up here, right? Because we're doubling that height now, right? So this graph is really, really, really steep, okay? So the second thing I want you to notice is that the graph increases well is that if we had instead, if we had the graph y equals 3 to the x, or y equals 4 to the x, or y equals 5 to the x, they're gonna behave in a similar manner, right? Because the only thing that would be different, raising 3 to the 0 power, that's still gonna be 1, right? Raising 4 to the 0 power, still gonna be 1. 5 to the 0 power, still gonna be 1, okay? So all of these graphs, right, these are all gonna go through the point 0, 1, okay, because anything to the 0 power is 1. And in terms of what they're going to look like, they all look really similar, right? It's just instead of going 1, 2, 4, 8, we would go 1, 3, 9, 27, right? The powers of 3. Over here, they go really steep. They get steeper even faster than this one. And on this side, it's going to flatten out because you've got that flipping going on. So it's still going to give you this asymptote over here, okay? So all of these graphs, they're all going to go through 0, 1, and they all look similar. They're all going to have this basic shape where they're going to go through slightly different points, but the same basic shape. All right, so then this next graph that we have here, y equals 1/2 to the x power. Okay, now first off, thing that I want to point out is that this is the same thing as if it was written y equals 2 to the negative x power. Okay, so that's the same thing. So either one of those graphs would be exactly the same. Great. Okay, so let's take a look at our table values for this one. So I'm going to do the same thing. I'm going to start with 0 in the middle. I pretty much always do that with exponential functions. Anything to the 0 power is always 1. Okay? When I raise this to the first power, 1/2 to the first power is just a half. 1/2 to the second power, that's 1/2 times 1/2, which is 1/4. Right? 1/2 to the third power, 1/2 times 1/2 times 1/2, that's 1/8, right? Okay. And then if I go the other way, if I use negative exponents, well, 1/2 to the first power is 1/2, and the negative makes it flip. So the 1/2 is going to flip and become a whole 2. Okay. If I raise it to the -2 power, well, 1/2 to the second power, we already decided was 1/4. The negative makes it flip, so it's going to be 4. 1/2 to the -3 power, 1/2 to the third is 1/8, and the negative makes it flip to whole number 8. Okay. So again, we see that sort of symmetry when we look at this graph. And when you compare these two tables of values, they're almost the same, right? It's just that the y values are going in the opposite direction. So they're very similar. All right, so let's take a look at our graph. So I'm going to start with -3, 8, because that's the easiest one. Oops, sorry, put that in the wrong spot. There we go. Okay, -2, 4, -1, 2, 0, 1, 1/2. And you can see that the shapes of these graphs are very similar. It's just one of them has been flipped from the other one. Okay? And you notice how it's a horizontal flip? Well, compare this form of this equation to this one, right? All we did was we added a negative in front of the x. And what does multiplying an x by a negative do? Well, it's a horizontal flip, right? We've done horizontal flips before. So that's what's going on in this graph. Okay? So, a couple of things that I want you to notice about this graph. First of all, I want you to notice that the graph of y equals 2 to the x and y equals 1/2 to the x, so these two graphs we just looked at, they are symmetric. There's a geometry word you haven't used in a while, right? Over the y-axis. They're horizontal flips of each other. All right, and then the next thing I want you to notice is that when you are raising, right, when you have this function set up where this base number, right, if it's greater than 1, right, then you're going to have an exponential growth function. If it's less than 1, right, but still has to be bigger than 0. So bigger than 0, less than 1, right? So a fraction that's less than 1, okay? Then you're going to have an exponential decay function. So if your base number is greater than 1, it's going to be exponential growth. It's going to get big over time, like the top one did. All right, but if b is less than 1, again, still greater than 0, that's going to be an exponential decay function. Okay, and then last, I just want you to make sure that you note that anytime you have a function y equals 1 over b to the x, that can be written as y equals b to the negative x. Those are the same thing. Okay, lovely. So now that we have our basics down, now we're going to look at how do we graph these using transformations. Okay, and the transformations are exactly the same as they have always been. Okay, they're not changing. It's just things have been shifted a tiny bit. Okay, so when we're looking at these, right, anything that's changing the x, that's going to be your horizontal stuff. If your x is negative, horizontal flip. Okay, if you have an x that's in plus or minus, that's a horizontal shift. Okay, and then any numbers that are added at the end, those are your up down. Okay, so when we look at this, you're going to have y equals, right, some a value times whatever your base number is raised to the x plus or minus some number, and then plus or minus some number, right? This guy, that's your left, right, still backwards of what you'd think it would be, just like always. This guy, up, down, right? This is your vertical shrink, stretch, or flip. And if there's a number in front of the x, that would be a horizontal shrink, stretch, or flip. Okay, note that your asymptote is also going to shift when we do these transformations. All right, and what we're going to do with these guys is normally, like all the graphs that we've done so far, when we've done a transformation, we've always had that sort of like center point that moved, right? Like when we did parabolas, the first thing that we would do is we'd mark, oh, okay, well, it went over 3 and up 2. Here's my new vertex, and then we graph from there, right? Okay, well, the problem with that is that these graphs, there's not a point at 0, 0. So when you do your transformations, you're not going to put a point at exactly where the new spot is. So what I do is I use a little X just to mark that spot so that I know where it is. Okay, so you'll see what I mean. So this guy right here, y equals 2 to the x, all right? This shift right here is going to take you down 3. Okay, so what I'm going to do is I'm going to come over here and I'm going to go down 3, but instead of putting a point, I'm just going to put a little X there, right? Because if I shift this graph down 3, it's this part that's shifted down to where 3 is, right? And there's no actual point there. All right, and then from there, I'm going to use this same table of values that we had before. Okay, I left space here to recopy it so that I would have a reference, but I'm on 2 different pieces of paper, so I don't need it. Over 3 and up 8. Okay, your asymptote is going to go right through that x. And on this side, here's my -1, 1/2, right? -2, 1/4, and so on. And there's my graph. I missed a little bit there. And that's it. All right, so let's take a look at this next one, the one below it, okay? Because I've still got the same table of values for this one. So looking at this guy, this x minus 3, that is going to be a left-right shift, and it's backwards of what you'd think. So instead of taking you to the left, it takes you to the right 3. So from my origin, I'm going to go right 3 and put a little x there. Okay, my asymptote is going to go right through that little x. And then from there, I can just graph the same graph. So 0, 1, 1, 2, again, starting from the x. So from the x, there's 0, 1. From the x, here's 1, 2. From the x, here's 2, 4. Right? And there's 3, 8. And then on this side, these points really don't have to be exact. I sort of eyeball the first one, try to get that approximately where it should go, and then just sort of make dots after that. They get closer to the asymptote. And that's it. All right. Let's take a look at this one down the bottom of the page. I'm totally going out of order here. Hope that doesn't bother you. Okay, so this guy, this one's kind of complicated. Or, okay, yeah, so let's not do that one yet. Let's do some of the less complicated ones first. So let's take a look at this guy over here. All right, so this one we're raising 1/3 power, right? So I'm going to make a quick table of values. This is something that you're going to want to kind of learn to do in your head. 1/3 to the 0 power is 1. 1/3 to the first is a third. 1/3 squared is a ninth. 1/3 times 1/3. 1/3 to the third is 1/27. These are just going to be flips. So if this is 1/3, that's 3. If that was 1/9, that's 9. If that was 1/27, that was 27. Okay, so there's our little table of values, and then this guy right here, that is an up 2. So here's my little x. My asymptote goes through the little x. And from there, I'm going to plot these, right? Here's 0, 1, right, from the x, over 0, up 1. 1/1/3 to be about there. 1/9, 1/27. Again, I just sort of eyeball little dots. Going this way, -1, 1, 2, 3. Don't forget, you're starting from the x. I know I keep saying that, but don't forget to start from the x. Okay, and then 9 would be somewhere up here-ish, right? Just give me an idea of how to draw this. There we go. Cool, all right, this guy down here. So y equals -2 to the x. So this guy, that is a vertical flip. So what we're going to do is we're going to go the opposite direction that we would have. Okay, so anytime you would have gone up, you're going to go down. Okay, or if it all right, so 0, 1, normally from the x we go left, right, 0, and up 1. But since we're doing a vertical flip, I'm going to go down 1. Okay, normally my next point would be over 1, up 2. But since we're doing a vertical flip, over 1, down 2. Okay, instead of over 3 and up 8, I'm going to go over 3. Oops, I missed a number. Sorry, I missed 2. Second power, 2 to the second power. So instead of over 2, up 4, I'm going to go over 2 and down 4. Instead of over 3, up 8, I'm going to go over 3, down 8. Okay, and then on the other side, instead of over 1 and up a half, I'm going to go down a half and then down a quarter. And there's my asymptote. Okay, so vertical flip just like we've been doing. All right, so now let's go down and hit these ones that are a little bit more complicated. All right, so I'm going to compare this. Here's my 1/2 table, just so I can use that as a reference. And we got a lot going on here, right? This guy is going to take me up 4. This guy, backwards of what it looks like, so that's right 3. And then this guy is a vertical flip. Okay, so first off, I'm going right 3 and then up 4. There's my x. Asymptote goes through the x. Okay, and now I'm just going to do my vertical flip. So when I'm plotting these points, normally it would be -3, 8. Well, I'm going to go -3, -8. Should be down here. Normally, -2, 4. Well, I'm going -2, -4. Okay, normally -1, 2. Well, I'm going -1, -2. Right? I'm changing the signs of my y values because that's what my horizontal component is. I'm sorry, my vertical component. Totally wrong word. There we go. All right, last one. This one, we got a 3 in the front. That is a vertical stretch. Lovely. So no transformations in terms of shifts. There's my x. Asymptote goes through the x. All right, so now what I'm going to do, again, we're going off of this table over here. I'll see if I can get them all on the screen at the same time. Right? We're going off of this table, right? But the difference is that now I'm doing a vertical stretch. So I'm multiplying my vertical component by 3. So I'm essentially taking these guys and multiplying by 3. So when I go to do this, 0, 1 is now going to become 0, 3. 1, 2, 3. Right? 1, 2, instead of going over 1 and up 2, I'm going to go up 3 times as far. So that puts me up at 6. Over 2, up 4, well, that would put me at over 2. Normally I go over 2 and up 4, but I can't do that. I have to go up 3 times. So that would be up 12, which is like, I don't know, up here somewhere, right? And then going this way, negative 1, 1/2. This is where it's a little bit tricky. So you go over 1 and up a half. We're going 3 times as far, so that would be 1.5, right? Negative 2, 1/4, well, 3 times. But you're just using the same transformations that we've done for the entire year. So that shouldn't be too much of an expense.